Welcome, math friends. We are going to be working with exponential equations today. Hopefully you've seen the exponential functions video and you understand the logarithmic and exponential relationship. We are going to be using logarithms to help us solve these exponential equations. Now, what we need to do is typically we will have some sort of exponent and we want to rewrite or take the log of both sides in order to solve for whatever the variable is. So we have a general strategy of making sure that we have the exponent isolated and then taking the logarithm of both sides, or we can rewrite in logarithmic form, and I will show you both. Notice here that I've said you can either take the logarithm of both sides or you can rewrite in exponential form. It just depends on the equation that you are given. When you have something that is some base to an exponent equal to something, you can rewrite that in logarithmic form. Otherwise, if it's a little bit more complex, you would want to take the logarithm of both sides and then using either condensing or expanding to solve. So let me show you the forms and how they relate as a reminder. If you have log base b of x that's equal to y, when you rewrite that in exponential form, that is the same thing as b to the y equaling x. And we're going to use the relationship between those two to solve. For the first problem, I'm asked to solve for k. And I notice that I have an exponent. So I have a base to an exponent equal to some number, which means because I have those three components, I could rewrite this in logarithmic form, or I could take the log of both sides, and I will do both. If I was to take the log of both sides, I'm going to use the natural log. You could use regular log or you could use natural log. Both get the same approach. This does have E and natural log work well together. So I'm going to use the natural log here. But if I took the natural log of both sides, remember the power rule of logarithms. If you have something to a power, the power can come in front and become a coefficient. So I'm going to write that as 2k natural log of e equals natural log of 4. But then remember that the natural log is log base e. So if I have log base e of e, e to the 1 is e. This evaluates to 1. Whenever you see natural log of e, that is actually just 1. That means I have 2k times 1, which is 2k, equals natural log of 4. Dividing both sides by 2 gives me that k is equal to the natural log of 4 over 2. Now, dividing by 2, that's the same thing as saying k equals 1/2 natural log of 4. I could then use that same property and actually make the coefficient the exponent, which is saying k equals the natural log of 4 to the 1/2, and 1/2 is the square root. That's k equals natural log of square root of 4, or k equals natural log of 2. Now, it depends on your teacher or your instructor what they're looking for. They might accept natural log of 4 over 2 or 1/2 natural log of 4. But if you were to use some sort of computer algebra system to help you solve this, and you got that it was the natural log of 2 and you didn't understand why, this is why. Things can simplify even further, but your instructor may not want you to go that far. So please be sure that you understand the expectations of whoever your teacher is. Rewriting this from exponential form into logarithmic form, I'm going to show you in a different color. The base exponent becomes the base of the logarithm. That's log base e, which is natural log. And then instead of writing log base e of 2k, it's actually log base e of 4 equals 2k. And remember, I'm solving for k, so I would need to divide by 2. I'm going to write log base e as natural log. That means I have natural log of 4 equals 2k, or natural log of 4 over 2 equals k, which is the same thing that I had here. Rewriting and taking the log of both sides are going to get you to the same place. It's just a matter of what you feel more comfortable with. Moving on to the next problem, we have e to the natural log of 0.8k equals 0.8. Well, let's rewrite natural log as log base e. That means we have e to the log base e of 0.8k equals 0.8. We're solving for k here, but if you recall, a base exponent to a log of that same base, those actually cancel each other out, and you're just left with the logarithm value of 0.08k. That means I have 0.8k equals 0.8. Dividing both sides by that 0.8 gives me that k equals 1. Moving on to our next problem. I have e to the 5k equals 1/4. In this case, I could rewrite this using logarithmic form, where I would take natural log of e 1/4 equals 5k and divide by 5, or I could take the natural log of both sides. I'm going to go ahead and take the natural log of both sides. That means I have natural log of e to the 5k equals natural log of 1/4. I'm going to do a few things here. Remember that the exponent becomes the coefficient. I'm going to rewrite that as 5k natural log of e is equal to natural log 1 minus natural log 4. And there's a reason that I did this. That is because I know that the natural log of 1 is actually a special value. You might not be familiar with it if you're just learning natural logs, but if you go back to the logarithmic properties, you can understand that the natural log of 1 is a specific value, just like the natural log of e is also a specific value. 5k natural log of e, we've already established that the natural log of e is log base e of e, which is the value 1. That means I have 5k times 1, or 5k, and then natural log of 1, if I was to rewrite that, I have log base e of 1, and e to the 0 is 1, which means that this value here is 0. Those are two logs you should be familiar with. You should know that the natural log of e is always 1, and the natural log of 1 is always 0. Those will come in handy when you're simplifying. Then I have 0 minus natural log of 4, or just negative natural log of 4. Dividing both sides by 5, I get that k is equal to negative 1/5 natural log of 4. I could take the coefficient and write it as an exponent and write that as natural log of 4 to the negative 1/5. I'm just going to leave it like this. That doesn't simplify to be some clean number, so I'm just going to leave my answer as k equals negative 1/5 natural log of 4. Moving on to this next problem, I have exponents on the same side of the equal sign, which is not going to help me when I'm taking the natural log. It just is a little bit more complex. You can do it. You would just need to use exponent properties to understand what that looks like. What I'm going to do here is I recognize right now that both of these share an e to the k. I could go ahead and move the 3e to the k onto the right-hand side and take the log, but first I want to see if I can get somewhere else by factoring out an e to the k. E to the 2k is not e to the k squared. 2k means k plus k. This is the same thing as e to the k plus k minus 3e to the k. Or e to the k minus 3e to the k equals 0. And the reason I say that is because I want you to understand that when I take out the e to the k, I'm still left with an e to the k. I'm not just left with 2. So if I factor out e to the k, I have e to the k minus 3 equals 0. And then using the zero product property, that means that e to the k equals 0 and e to the k minus 3 equals 0. Or e to the k equals 0 and e to the k equals 3. And then I can go ahead and take my logarithms or rewrite them in logarithmic form. E to the k, no number to an exponent is going to give me a 0. So e to the k does not work for me. If you saw that if I took the natural log of e to the k equals natural log of 0, I cannot take the natural log of 0. That's an undefined value, so this is not going to work out for me. But if I was to take the natural log of both sides here, I would get the natural log of e to the k equals the natural log of 3, or k equals natural log of 3. I could have taken natural log 3 equals k just by rewriting it into exponential form, but I went ahead and took the log of both sides. If I was to take e to the 2k equals 3e to the k and took the natural log of both of these, I would then have 2k equals natural log of 3 plus natural log of e to the k using multiplication, or 2k equals natural log 3 plus k. Subtracting k from both sides gives me k equals natural log of 3. So I could also approach it that way. It just depends on understanding the way that condensing and expanding works and how familiar you are or comfortable you are with the different techniques. Moving on to the next problem. We have a little bit of a complex situation here. We've got a square, but notice we're supposed to be solving for k and I have x here. I don't know what x is, which means I'm going to have x in my final answer. And so the way that I'm going to approach this is by taking the log of both sides, but I want to combine the exponents on the left-hand side. And since they are together, that's actually a plus. It's not going to be x squared times 2x plus 1. Exponent rules say multiplication is actually addition. That's going to give me e to the x squared plus 2x plus 1 equals e to the x. That's a perfect square trinomial. I could actually rewrite that as e to the x plus 1 squared if you were to factor that. Taking the natural log, I get the natural log of e to the x plus 1 squared equals the natural log of e to the k. Both of those pieces actually come out of the exponents, which means that x plus 1 squared equals k. And that is my final answer. I hope these examples helped you determine which way you would want to solve different exponential problems and help you feel a little bit more comfortable. Have a great day. Thanks for watching.